Hello, in this video I'm going to explain the solution for question number 5 in the problem set for slope stability analysis. As you can see here in the given diagram, it's about a slope of clay soil. So the density, the saturated density and the cohesion for the soil is given, and also you can note that there is a tension crack. So from the line CD, it represents a tension crack, and all the other information, center of gravity, the location of the center of gravity as well as the area, all the required information are given for the stability analysis. The part A of this question talks about a scenario where the channel is completely filled with water. So the water level matches with the top of the slope. So in this case, there are two things to be noted. So since the slope is fully submerged, so when you're going to calculate the stability or the weight of the soil, you need to use the submerged unit weight instead of the saturated unit weight. The second point to note here is, since there is a tension crack, so when the water level is up at the right top of the slope, the tension crack is fully filled with water. However, the water pressure that will be applied by the water within the tension crack will be negated by a similar amount of opposite pore water pressure that comes from the water within the channel. So therefore, we do not need to consider water pressure comes from the tension crack when the water is fully filled within the channel. So now therefore we can calculate the factor of safety against the slope failure. So that will be the resisting moments divided by the disturbing moments. So we can calculate the resisting moments and the disturbing moments separately and then substitute in this equation. The resisting moments comes from the strength of the soil. So since it is a cohesive soil with friction angle of 0, it will be the cohesion provides the resistance. So the cohesion is given as 35 kilopascal, and then you need to multiply this one by the length of the slope arc, the failure arc. That will be, we calculate using the radius of the arc times the angle. Radius is 15.75 and the angle is 95.5. However, this 95.5 is given in degrees, so when you substitute in this equation, it has to be in radians, so therefore it has to be multiplied by pi over 180. And then to calculate the resisting moment, this is the resisting force, you have to multiply it by the distance again, that will be the radius again, which is 15.75. That will be your resisting moment. That will be 14,471 kilonewton meter. That will be your resisting moment. Now you can calculate the disturbing moment. So the disturbing moment comes from the weight of the soil. As I explained before, since the slope is fully submerged in water, you have to use the submerged unit weight of water to calculate the weight of the soil. So the unit weight of water, so therefore we are going to use submerged unit weight times the area times 1. So we are looking at a 1 meter thick section, therefore the cross sectional area has to be multiplied by the length, which is 1 meter, to get the total weight of the soil from the unit weight. And then you need to multiply this one by the perpendicular distance. You can see that this weight will be acting from the center of gravity. So the center of gravity is 3.2 meter away from the center of the circle. So therefore you need to multiply this one by the perpendicular distance 3.2 meter, which is the perpendicular distance from the center to the weight of the soil. So that will be, so the submerged unit weight you calculate from gamma saturated minus gamma W times A times 3.2. So now you can substitute the values. So the gamma saturated is the unit weight of the saturated soil. So the unit density of the saturated soil is given as 1900. So we can multiply that one by 9.81 to get the unit weight of saturated soil. So you need to divide that one by 1000 to make it kilonewton per cubic meter. So otherwise it will be in Newton per cubic meter. To be consistent with other units, I will divide it one by 1000. The unit weight of water is 9.81 and the area is given as 155 square meters, and then the distance is 3.2. So that will give you a resisting moment of 4380 kilonewton meter. So now we have calculated the resisting moments and the disturbing moments. From that, now we should be able to determine the factor of safety, which is the resisting moment 14,471 divided by 4,380. So that will be 3.3. So the factor of safety of this slope when the channel is fully filled with water for the part A is 3.3. Part B of this question asks you to calculate the factor of safety for the same slope when the channel is empty. So when you have a slope for this kind of a channel, it is very important to calculate the factor of safety considering both scenarios, when the channel is fully filled and also when the channel is empty. So now in this part, since the channel is empty now, there is no force that will be acting opposite to the pore water pressure, or the pressure comes from the water within the tension crack. Therefore, in this case, we need to consider the water pressure comes from the tension crack. So the tension crack is the CD part. If you have a tension crack like that, and when it is filled with water, so the water pressure varies linearly. And at the bottom of the tension crack, the pressure we can calculate using gamma W times Z. The pressure here is gamma W times Z. So the gamma W is 9.81 times the height of the tension crack is 2.92, and there will be pressures at all depths. So therefore the total force comes from all these pressures, which is the resultant force, can be calculated by calculating the area of this pressure diagram. So the area of this pressure diagram will be half. So this tension crack height is 2.92. Therefore half times 9.81 times 2.92 is the base length multiplied by the height 2.92. So that is the force comes from the pore water pressure. So that will be 41.8 kilonewton, and that will be acting at the center of gravity, so which will be here 2/3 of the height, which is 2.92. Now, so we know the additional pressure that should be accounted in this case. And the other point here is, since under this condition, since the slope is not submerged, so we will have to use the saturated unit weight. And now we can calculate the total disturbing moment and also the resisting moment. However, when you are going to calculate the disturbing moment, you will need to know the distance, the perpendicular distance from the center of this circle to this pressure, the force. Therefore, we know that it is from the top of the slope, it will be 2/3 of 2.92, but we also need to calculate the distance from the center. So if you look at this diagram again, you can see that the distance AL we can calculate using the trigonometric relationships. That will be 7.5 divided by tan 30. So that will be 12.99 meter. And we can also calculate from this now AK length. The length AK will be AL minus 3, which will be 9.99 meter. Now when we know the AK value, so we can apply the Pythagoras theorem to calculate the length OK. Length OK, which will be 15.75 squared minus 9.99 squared and the square root of that. So that will be 12.18 meter. And now the total, the vertical distance between O and C is 12.18 minus 7.5, which is 4.68 meter. 4.68 meter. Now we can now determine the moment arm for the water pressure, water force, for the water force. That will be this 4.68 plus the 2/3 of 2.92, which is 1.95. That will be 6.63 meters. So that is the moment arm. So that is important to calculate the moment. So the disturbing moment comes from the water pressure force. Okay, now we have calculated the water pressure force, and also we can now calculate the self weight of the soil, and then all the disturbing force, disturbing moment. So let's calculate the disturbing moment, the total disturbing moment, disturbing moments. So we can have two components, soil weight. So remember, so the soil is no longer submerged, so therefore we are going to use the saturated unit weight instead of the submerged unit weight we used before for the scenario where the channel is fully filled with water. So now the saturated unit weight can be calculated using the given density, which is 1900 multiplied by 9.81 divided by 1000 to make it kilonewton per cubic meter, and then multiplied by the area, which is 155, and then the perpendicular distance will still be 3.2. So the only difference compared to the last part is now we are going to use saturated unit weight instead of the submerged unit weight, considering the situation. So now this this moment will be 9244.9, and there will be another component coming from water pressure in the tension crack. Water pressure in the tension crack. So we calculated the value as 41.8 kilonewton, and then multiplied by the perpendicular distance we calculate as 6.63, which will be 277.1 kilonewton meter. So this will be also in kilonewton meter units. So its total disturbing moment will be the summation of these two. And now we can also calculate the resisting moment. Resisting moment will still be provided by the strength of the soil. So in this case we have a cohesive soil, therefore the cohesion of the soil will provide the strength. So we calculated this strength before for the part A, so we can still use that value because there is no change for the resisting moment. So we calculated that one as 14,471 kilonewton meter. So the resisting moment is not going to change whether it is for the channel is fully filled or empty. So now we can simply calculate our factor of safety, which will be resisting moments divided by disturbing moment. the resisting moment is 14,471 divided by 9,244.9 plus 2,277.1. So that will be 1.52. So now if you compare the two situations, when the channel is fully filled with water, the factor of safety was more than 3. So now it has gone down to 1.52. So from 3.3 to 1.52. So therefore the critical case, so the critical scenario, the most critical condition will be not when the channel is fully filled, but when it is emptied. So those two values gives that indication about the stability of the slope.